How's it going, guys? It's Mr. Verdi here again. We're going to talk about action potentials in a little abridged PowerPoint that I have made for you guys. The whole thing we post online too. So here goes. Okay. Uh, First off, let's look at the forest. Okay. The forest. When we look at neurons, neurons are highly irritable. I don't know if you guys know this person. I didn't know her until she sat behind me on a plane after my honeymoon. Her name is Janell. She's a crazy teen mom from MTV's hit shows, Teen Moms 2. And I didn't know who she was until Mrs. Verdi said, Mr. Verdi, that's Teen Mom 2, Janell. I said, who's that? She said, she's crazy. And she was crazy. She started screaming at someone on the airplane that I was on. I was so excited. Okay, so anyways, neurons are irritable like Janelle from Teen Mom 2. Okay, irritable meaning they'll respond to stimulus. Okay, if we stimulate a neuron, it will respond. The key thing to know is its response, if the stimulus is strong enough, is an action potential. Here's the word I'm looking at. Oh, shoot, sorry. Okay, that is other words sometimes called a nerve impulse, but action potential is what we're studying today. Okay, no matter what, when a neuron's stimulated, the action potential is always of the same strength. Okay, and hopefully we get that clear over the next couple days. Okay, so that's the forest, right? Neurons are irritable. They respond to a stimulus by having an action potential. Now here come the trees, right? There's the big picture. Let's make this crazy. So first off, you don't have to know physics. Space isn't a thing, time isn't a thing, but space-time is a thing. It's fascinating, but you don't have to know it for our purposes, okay? But we'll be using some of it. Talk to Mr. Rice. So a little bit of electricity. Opposites attract. If you guys are Bachelor fans, you know that Pete and Madison were not the right mix for each other. Okay, she seemed like a good person. I think Pete was a good person too, but they had some different values, right? My Bachelor fans out there, okay, basically Kelsey. Okay, so anyways, yeah, read this slide and energies liberate when charges move towards one another, yada, yada, yada. Like I said, no, no physics, but it's there. So here's the big one that we're going to look at, okay? Here's the big picture, all right? This is the graph of, in general, an action potential, okay? And you're going to have to know what's happening along the cell membrane at these four spots, okay? And you're going to have to know your neuron at rest, so hopefully you've studied that pretty well. But here goes. At rest, our sodium-potassium pump is really the only thing that's working, pumping sodium ions out of the cell and potassium ions into the cell. When stimulus is strong, here's rest, okay? Well, this could be going on for the whole time until it's time for that neuron to send a signal. And if that neuron gets a strong enough signal, it's going to open up sodium voltage gated channels. Okay, so sodium channels open up. Well, what happens when a sodium channel opens up? Remember, there's more sodium outside the cell than there is in. So when a sodium channel opens, sodium floods the cell. Okay, it goes down its electrical and chemical gradient. Electrical, because remember, the inside of the cell is negative, the outside of the cell is positive. So sodium is going to go towards those negatives. Remember, opposites attract. Okay, what happens when you get a whole bunch of more positive things inside your cell? Well, it becomes more positive. This y-axis is a measurement of the voltage of the membrane, right? And so the cell started negative, but as sodium comes in, it's going to get more and more positive. The sodium voltage gated channels are very, very quick to act. So they open, look at this, we're talking, fractions of a millisecond and how quickly they open, but they close just as quick. So the sodium voltage gated channels close, no longer can sodium come in or out of the cell, repolarization starts to happen. Well, how does that happen? It has to do with potassium ions. Potassium channels get the same message at the same time, but they're slower to open. So potassium channels open. Now remember, potassium is highly concentrated inside the cell compared to outside the cell, which means there's a chemical gradient that causes potassium to move outside of the cell. We've also generated an electrical gradient because with all that sodium in the cell's flipped to positive. So when the potassium channels open, there's two forces, an electrical and chemical, urge, maybe I don't want to use the word force, but appealing, whatever. There's an electrical chemical gradient that causes potassium to leave the cell. Okay, again, see your physics teachers for force. All right. Now, potassium leaves the cell. Well, what happens when a positive leaves your life? Okay, when something positive leaves your life, you get more negative. Okay, so you get more and more negative. Now, the potassium channel is almost like this lazy thing, right? It opens late and it closes late. We actually hyperpolarize. We let too much potassium out of the cell. I say we, I mean the neuron, right? Um, the neuron lets too much potassium out of the cell and actually has this overshoot period where it might even drop to like negative 90 millivolts, right? Causing this thing called hyper or over polarization. All right, this is important for a little lesson later. Okay, hopefully we can get there to this distance learning thing. Deal? Eventually, resting membrane potential is restored thanks to sodium potassium pump, and if there's nothing else going on, the cell will return to this negative 70 millivolt resting state. Okay, guys? So, action potentials, what do I want you to know? What's happening at each of these little numbers? Okay, we can look over here. This is a great little graph. I love this one. Okay, the old two y-axes. The relative membrane permeability is going to apply to these two lines, right? Sodium potassium permeability. It's hitting the message home. Okay, it's going to relate to, well, what's causing what? All right, and again, what you can see is when the cell is most permeable to sodium, the cell will turn slightly positive along that membrane, right? Because sodium's flooding the cell. Now we can look back at the y-axis on the left side when that happens, and we see this increase in membrane potential. Cool. You can see the delay, right? The potassium delay in increasing impermeability. This is evolutionary super important. This is not by accident. This was highly selected for. And it's like this in all creatures, big and small, okay, that have neurons. Deal. So this potassium permeability is slower I should say the potassium voltage gated channels are slower to open, but once they do, notice how long the cell's permeable potassium, a lot longer, well, almost maybe twice as long, okay, as the cell is permeable to sodium. And that causes this hyperpolarization, this overshoot. Okay, guys, that's all I got. Just a reflection. ESPN played last night. There are happy times before and happy times are ahead, kids, right? One day we'll see each other in person. It'll be so nice, and we'll be so grateful for that. Until that day, stay isolated and have a great day. And let's see here. Now here comes the part where I have to stop this.